Okay, I think this is going to be the last video for Lecture 15. Wherever this one ends up is where we'll stop for this one. So we were introducing the concept of a refrigerator. I'm starting at the compressor. Again, your text likes to draw a piston cylinder. I like to draw a turbo compressor, the reverse of a turbine. So the output's coming out of where it gets squeezed down and coming out this end. It gets squeezed to a high pressure. And we just talked about when you squeeze a gas, a lot of times the temperature will increase. And this is really kind of what we're after in a refrigerator. We want both the high pressure, but more importantly, we want this high temperature. I like to say we get this refrigerant screaming hot. We get this refrigerant so hot that when we run it through the condenser coils, this is a heat exchanger. And we get the refrigerant so hot that when we expose it to a high temperature source, it's hotter than the high temperature source. So it will, and it's not a source, it's a reservoir. You got a reservoir operating at a high temperature. And we have this thing so hot that it will actually lose heat to that high temperature reservoir. Okay. If you walk by the outside of an air conditioning system, right, the little tower that sits outside with the fan in it, or if it's a window unit, the coils, the aluminum fins on the outside, you walk by one of those when it's running, and what do you feel? You feel this heat. This device, that's the condenser coils. Refrigerant's flowing through there, it's going to push air through there, and that air is used to basically remove heat from this refrigerant into normally the air, the outside air, or in the case of your refrigerator in your house, the air inside your kitchen. So it's removing heat to a higher temperature source. Now, it's going to come out high pressure. Nothing in that process is going to change the pressure. At least we're going to assume there's no major pressure drop. It's going to be roughly the same pressure coming in as it is going out. But it's going to be kind of a lower temperature. We've removed heat from this refrigerant, so it's not at a high temperature anymore. It's going to probably drop down to a lower temperature. It might even get down to a liquid or even a mixture. And then we're going to run that through a kind of a magic process we call an expansion valve. I actually had a guy come talk to one of my intro to engineering courses not that long ago. He just passed his a former student of mine passed his professional engineering exam. He's an HVAC engineer. He works on air conditioner systems. And he even calls this kind of a magic process. It's the magic that goes on. What happens here? If you allow a high pressure substance to expand, you run it through what we call an expansion valve. What happens? Well, the pressure drops. And as the pressure drops, so does the temperature. Now, how do we know this? Well, one example I can give you is you could take a can of that, and I should grab one and have it handy. You know the aerosol that you can use to clean your electronics? They call it compressed air. It's not air. It's a compressed substance. And if you hold that valve open, if you hold that spray nozzle open for a long period of time, what happens? It gets really cold. Right? So if you allow a compressed substance to expand to a lower pressure, in the case of that aerosol can, you're allowing it to go from the high pressure inside the can to the low pressure outside, and the contents inside the can is going to a lower pressure. So as it's doing that, it's expanding. And through that expansion, it's basically doing boundary work out, getting it to a lower energy state, a lower temperature. So through this expansion process, we reach a lower temperature. And the goal here is to get the substance to such a low temperature, get it so cold that it will actually absorb heat from my low temperature reservoir. So I've got a reservoir down here operating at a low temperature. And we called this set of coils, this heat exchanger, the evaporator. You normally don't see the evaporator coils in your refrigerator or your air conditioning unit. If you've got an air conditioning unit and you change the filters, the air filters on it, you might see the evaporator coils. They're typically smaller than the outside condenser coils, but they're cold. And if your system's not operating correctly, they can actually freeze over. But again, you normally don't see these in most modern devices. They're kind of hidden away within the device. But the goal here is to get it so cold that it will actually absorb heat from the source that you're trying to cool. Right? And then the process is ready to go back into the compressor. So you come out of this still low pressure, and I would suggest low-ish temperature. Right? But you really want this to evaporate off. You want vapor going into the compressor. If you don't have vapor going into the compressor, you can't compress liquid. It just doesn't work. So we got to put in enough heat to evaporate all of the refrigerant off into a vapor phase at a low pressure, low temperature. Then it can be compressed up to a high temperature, high pressure, and the process is ready to repeat. That's how refrigeration works. Okay. Again, notice, just like we did with the heat engine, what's my system boundary? It's this gray shaded in area. It is a closed system, right? Because it's a closed system, if we do first law analysis, if I do first law analysis on this, this is a closed cyclic, it's a closed cyclic system. It's operating in a cycle, right? So again, En minus E out is equal to delta E system. Because it's a cycle, this goes to 0. So we add the ins, subtract the outs. What have I got going in? I've got work coming in. I've got QL coming in, minus QH going out. It's a cyclic system, so the change is 0. So what have I got here? I've got the work in is equal to essentially the net heat out. That's QH minus QL. And this is what the first law simplifies down to. Now, when we talk about a refrigeration device, we normally don't talk about its efficiency. We talk about its coefficient of performance, the COP. It's like an efficiency as it measures essentially the output of the device divided by the input. It's not a true efficiency because it can and often does exceed 100%. But if we think about what do we want out of this device, what is the goal of a refrigerator? Right, pause here and think about that. Pause. Which of these quantities, what going on here is the goal of this refrigerator? So pause it and think about that. Okay, so what is the goal? What is the output? What are we trying to get out of this thing? That's your goal of your refrigerator, is get QL. Right? So the COP, the numerator, that numerator, should not write right-handed, but that's actually not terrible right-handed. The numerator is QL, right? That's my output. That's the goal. That's what I do. That's what I'm after here. Now, what do I have to do to get this output? This is what I'm paying for, right? That's my electricity, if you will. That's what runs the device. The work input going into the compressor, right? Which was what we got here, right? COP is QL over the work in, or the net work in this case. Okay. When we say net work in, you could, in really large systems, they'll actually put a turbine over here, and you could actually get a little bit of work out to power some smaller devices. But you don't see that in most devices because it's another moving part to fail. This is really the only moving part in a normal residential refrigeration system, and so this is really about the only thing that's going to fail unless one of these ruptures. So anyway, but you could put a turbine. Anything that will drop the pressure from here to here, and maybe even drop the, and you do need a temperature drop. We need this so cold that it will absorb heat from the low temperature source. So whatever you want to put in here that'll drop the pressure and the temperature to where this will cycle is okay. A turbine will do that. But again, it's a lot easier to just put an expansion valve. There's no moving parts here. It just squeezes it down to the speed of sound, then allows it to expand, and magic things happen when you do that. It's not really magic, but it's kind of like electricity. We understand what's going on there, but it's another course. Okay? Okay, where are we at? So we talked about coefficient of performance. That's where we're at. So I'm going to write this as I'm expecting you to write it in your notes. Coefficient of performance. COP for a refrigerator specifically. What you want divided by what you have to put in. Now remember this guy over here. We said this is the first law. We said work in is also equal to QH minus QL. So I can also say that this is equal to, substituting in the first law here, this is QL over, what do we say, QH minus QL. Okay, and if I divide every one of these terms by QL, so the COP for a refrigerator, we can always find this way, QL over work in, that's always true. But if I take this expression here and divide everything by 1 over QL, divide everything by QL. Well, QL over QL is 1. This is over QH over QL, minus, and again, this is QL over QL, so it's just 1. So this is also true. Just like we saw earlier, I'll go back a couple pages, we said the efficiency, the thermal efficiency for a heat engine, I can write as an expression of a ratio of heat transfers. I can do the same thing here. The coefficient of performance for a refrigerator, I can write as a ratio of the heat transfers, and that's going to be important a little bit later when we talk about ideal cycles. All right, what's next? And here is what I've just derived there. So we're going to go ahead and skip that. Okay. Let's knock this out and we'll call this done. So let's talk about the 3 devices we want to talk about, the 3 cyclic devices we want to talk about: heat engine, refrigerator, and then let's talk about a heat pump. So what is a heat pump? A heat pump is where somebody, just like I told you guys earlier, if you walk by the outside coils of that condenser, what do you feel? You feel this heat coming off of those. So the outside part of your refrigerator, your air conditioner, you walk by that, you feel the heat coming off. Or if you feel behind your refrigerator or your freezer in your kitchen when it's running, you feel the heat coming off. That's QH. Somebody said, hey, what if we spun this thing around? And I use this to heat my house by cooling the outside air. That's a heat pump. A heat pump is when you turn a refrigeration cycle around. You use a refrigeration cycle to remove heat from a cold body and use that energy to heat a warmer body. You pump heat in the direction it does not want to go. It's the exact same device. Right? If we don't have to draw it in detail. Right? We don't have to draw it in detail. I'm just going to draw some shapes here. And again, the goal here is you want heat to go to your high temperature reservoir. Right? Probably like your house. Can I get this in? Okay. You're going to have to put work in. And what it's going to do is it's going to absorb heat from the outside at T sub L. All right, guys. That's where we'll pick up next time. Okay? See you.